Hello and welcome. Today we're diving into thermal energy storage, or TES. Think of it as a thermal battery, a way to capture heat or cold now and use it later. Why is this so important? Well, it helps us manage energy resources better, especially with renewable sources like solar and wind, which aren't always available. TES bridges the gap between when energy is produced and when we actually need it, making our energy systems more efficient and reducing our reliance on fossil fuels. It works on different scales, from your home water heater to massive industrial systems, and can store energy for hours, days, or even months. So how does it work? There are three main methods. First, there's sensible heat storage, or SHS. This is the most common type. You simply heat up or cool down a material, like water, molten salt, rocks, or concrete, without changing its state. The heat stored depends on the material's capacity, the temperature change, and how much material you have. Think of large water tanks for hot water or the molten salt tanks used in big solar power plants that allow them to generate electricity even after sunset. Second, we have latent heat storage, or LHS. This method uses materials called phase change materials, or PCMs. These materials absorb or release a large amount of heat when they change phase, like melting from solid to liquid or freezing back again, all at a relatively constant temperature. This latent heat stores much more energy in the same volume compared to just changing temperature, making LHS systems more compact. Examples include paraffin waxes or special salt hydrates used for heating or cooling buildings. Third is thermochemical heat storage, or TCS. This is a more advanced approach using reversible chemical reactions. You use heat to drive a reaction one way, storing energy in the chemical bonds. Later, you reverse the reaction to release the stored heat. TCS has the potential for very high energy density and long-term storage with minimal heat loss, but it's generally more complex and less mature than the other two methods. Designing these systems involves choosing the right materials, ones with high heat capacity or latent heat, good heat transfer, stability, and low cost. Engineers also need to design efficient heat exchangers and good insulation to minimize energy loss. Integrating TES smoothly with energy sources, like solar collectors or industrial waste heat, and the end use, like building heating or power generation, is also crucial. Where is TES used? We see it in buildings for hot water and space heating or cooling. It's essential for concentrated solar power plants, enabling them to operate around the clock. Industries use it to recover and store waste heat. And increasingly, TES is being explored to help stabilize the electrical grid by storing excess renewable energy. Recent developments focus on making TES cheaper and more efficient, developing solutions for longer storage durations, days or seasons, better utilizing waste heat, and even creating hybrid systems. However, challenges remain, including costs, material degradation over time, and the complexity of system control. Despite these hurdles, thermal energy storage is a vital technology for building a sustainable energy future. Continued innovation in materials and engineering will be key to unlocking its full potential. Thanks for tuning in.